Hello everyone, my name is Hassan Iqbal and today I am presenting our work Dissecting Cloud Gaming Performance with DECAF. This work is in collaboration with my two esteemed colleagues, Aisha Khalid and Mohammed Shahzad. So last few years have seen tremendous growth in the cloud gaming platforms. Um, its commercial success has made it a billion-dollar industry, and large internet organizations such as Google Stadia, Amazon Luna, and NVIDIA GeForce Now have launched their own dedicated platforms. So essentially, cloud gaming works by situating game processing logic in the cloud server, where the user commands are received, processed, and the response is sent back in the form of a video stream back to the client. However, there are some challenges with this architecture. It adds additional delay component to the whole gaming experience, and the performance of internet paths starts affecting the video stream that is coming to the client. So there is a need of a measurement methodology to analyze the performance of these platforms because there are various stakeholders interested in it. Users are interested in knowing which platforms to choose, which one is performing better. Cloud game service providers are interested to know the shortcomings of their platforms. And research community is interested in understanding and improving the state-of-art real-time streaming applications. There are some existing approaches, but there is a dearth of a systematic measurement methodology. There is a stream of work by ITOT on modeling quality of experience for cloud gaming. However, the key limitations are two. One, it lacks generality, where it is unclear whether the given model can be applied to different games and genres. And in measuring delay, it only incorporates network delay, whereas cloud gaming has several other delay components. Therefore, our goal is to present a systematic methodology that is general, that works across different platforms and genres. It is automated, that enables data collection without human intervention, and it is comprehensive, that it measures different delay and streaming matrices. Therefore, we present DECAF, which is a general, automated, and comprehensive methodology to dissect cloud gaming performance. Now, I will dilate on our methodology of how we measure delay and streaming matrices. So, broadly, we see three delay components: client end, network, and server end delay. When we combine all of these three components, we call it a game delay. So essentially, game delay is the time taken between the action taken by the user and its response when it displays on the client end. Let's take an example of first-person shooting game where the click of the mouse is the action and that user takes to fire the gun, and the response is the flash of the gun that is displayed on the client end. So this time difference between the action and the response is the game delay. Now, measuring this delay manually is very tedious, so we automated this process. First, we made a game bot that plays the game by moving the character around in the game environment and repeating the actions periodically. And while doing this, GameBot also captures the whole gameplay at 144 FPS, which is more than twice the rate at which the game is played. So it is capturing the timestamps for each frame as well as for the actions taken. Now, all we have to do is extract these response frame, match them with the actions, and calculate the game delay with the timestamps. However, doing this manually is again very tedious because in 10 minutes of gameplay, we have in excess of 86,000 frames. So we leveraged deep learning and trained a model based on response frames and which can extract these frames from the gameplay video. And we achieved more than 99% accuracy, and we show in the paper that achieving such an accuracy is possible even with as low as 100 frames. And we refer the interested readers to the paper on how we trained our model. Now, extracting the other delay components of game delay. So we instrumented the Chromium browser to extract network round-trip delay, jitter buffer delay, client end decoding, and rendering delay. When we subtract all of these delay components from the game delay, we get a server end processing delay. To measure the streaming metrics, we also instrumented the Chromium browser, where we captured bitrate, frame rate, resolution, and freeze metrics. Jumping to our measurement experiments, we use DECAF to measure the performance of Google Stadia, Amazon Luna, and NVIDIA GeForce Now. On each of these platforms, we played 3 different games belonging to 3 different genres: first-person shooting, action adventure, and racing. To measure the delay, we played the game at 3 different times of the day and repeated this for 7 days. And to measure and we also deployed DECAF at 3 different geographic locations to ensure that our results are not biased by our geography. To measure the streaming performance, we used an open vSwitch as a bridge between the client and the server to control for 2 network conditions. First, we congested the network bandwidth. We constrained the network bandwidth to see how well these platforms perform under limited bandwidth. Then we congested the network by introducing packet losses to see how these platforms respond to the lossy network. In our analysis, we analyzed game delay performance and streaming separately. In delay performance analysis, we analyzed 6 different delay matrices such as game delay, server end, network round trip, and so on. In streaming performance, we analyzed 4 streaming matrices such as bitrate, frame rate, resolution, and freeze. First, let's discuss the game delay performance and its components. On the x-axis, we have time in milliseconds. On y-axis, we have the platforms, and each individual figure represents game delay and its components for a specific genre: first-person shooting, action adventure, and racing. The combined length of these bars represents the game delay, and each individual bar represents a delay component, such as blue color represents the server end delay, and so on. Now, when we look at this figure altogether, we see that game delay not only differs across genres, but across platforms as well. Speaking of components, server end delay is the dominant component of the whole game delay, amounting to as much as 73% in case of action adventure game played on Luna. Server end delay also appears as a function of game genre. For example, when we were playing games on Luna, we found that server end delay on action adventure genre was 2.5 times more as compared to the racing genre. Also, server end delay differs across platforms for the same genre. While playing a first-person shooter game, we found that server end delay was 43 milliseconds more on Luna as compared to GeForce Now. Rendering and decoding delay were relatively consistent across all the platforms and genres because it is tightly coupled with the client end. However, jitter buffer delay varied a little. It was lower for Stadia, but a bit higher for Luna and GFN. Network delay was relatively similar throughout our experience. Now, we deployed DECAF at 3 different geographies to observe the delay performance. Our parent location is Raleigh, North Carolina. We also deployed DECAF in Boston, Massachusetts, and Los Angeles, California. We used NextMind and traceroute to localize the servers that were connected to our clients, and found that for each of these platforms, the servers were different. They were geographically close to the client. We couldn't localize the servers for Stadia, but our ping experiment suggests that the servers connected to the Stadia client were also very close in proximity to the client. When we look at the game delay and the network RTT performance, we see similarity across different locations for the same genre on the same platform. For example, in case of network RTT, the maximum difference we observed was 20.5 milliseconds between Raleigh and Los Angeles while playing action adventure game on GeForce Now. Similar results were seen for game delay, where the maximum difference we observed was 26.7 milliseconds between Raleigh and Boston while playing a shooting game on Luna platform. Now let's discuss the streaming performance in bandwidth constrained environment, and let's look at the bitrate performance. Now in this figure, on the x-axis, we have time in seconds. On y-axis, we have bitrate in Mbps. The blue line represents the bandwidth limit that we applied using Open vSwitch, and the green line shows the per frame bitrate that we observed during the gameplay. So overall, we can tell that all the three platforms differ in their delivery strategy. Luna and GFN have a similar sawtooth pattern, but GFN has more variation in its sawtooth pattern. So in sawtooth, the platform gradually ramps up the bitrate, and when it reaches the bandwidth limit, it abruptly drops the bitrate while ramping up again. In case of Stadia, we observe a probing pattern where the platform probes for the bandwidth limit and then drops significantly. So overall, we see an inefficient utilization of the available bandwidth across the three platforms. So we investigate utilization of bandwidth further, and towards this, we analyze the percentage of time a platform was able to deliver bitrate corresponding to different levels of applied bandwidth limit. In particular, we analyzed 4 utilization levels of applied bandwidth limits that are 90, 85, 80, and 75% utilization of the bandwidth limit. So a number of interesting aspects stand out. First, we see that all of the three platforms struggle to achieve high bandwidth utilization. At 90% utilization is achieved for less than half of the gameplay time. Similarly, at 75% utilization, the platform struggles to achieve high utilization. Stadia, in particular, appears very conservative. For Stadia, we also observe very large interquartile range throughout the gameplay, whereas the interquartile range for Luna and GeForce Now was smaller than Stadia. Now, this suggests that Stadia utilizes the available bandwidth quite conservatively and also has significant burstiness in its traffic patterns. Hence, to ensure consistent high quality of experience, users may need to provision their internet connection well above the recommended limit of 2 Mbps suggested by Stadia, 20 Mbps. Now, let's look at the frame rate resolution of first-person shooting game under bandwidth constraint environment. So on the x-axis, we have the bandwidth limits in Mbps. NL means no limit. On left y-axis, we have the frame rate as FPS, shown in green. And on right y-axis, we have resolution percentage, representing the percentage of time a game was streamed at a particular resolution, such as 1080p or 720. When we look at the Stadia performance, in terms of frame rate, it was consistent at 60 with some variation when the bandwidth switches. However, Stadia switches to 720p resolution when the bandwidth limit reaches 25 Mbps. Now, 25 Mbps is still higher than the recommended limit of Stadia to stream the game at 1080p at 60 FPS. And going down with the tighter bandwidth limits, the percentage of time game streamed at 720p significantly increased. Luna underdelivers on FPS and resolution, especially the FPS, where we observed very high variation in the frame rate. And we also observed that Luna strictly switches to 720p resolution when the bandwidth limit reaches 12.5 Mbps, which is still above the recommended limit. In case of GeForce Now, the resolution delivery was quite poor, although it was consistent at 60 FPS with less variation. But in case of resolution, even when there is no limit applied on the bandwidth, we saw a significant time game streaming at 720p. And going down the hill, when the bandwidth limit becomes tighter, we also observe streaming at 540 resolution, which we didn't observe for Luna and Stadia. Now, let's look at the streaming performance under congested or lossy network. So I'll talk about the frame rate, resolution, and freeze for action-adventure genre. On the x-axis, we have the loss percentages. NL means no loss. On the left y-axis, we have the bit rate shown in the blue color. On the right y-axis, we have two metrics. Frame rate as FPS shown in red and freeze counts shown in green. So just by looking at these figures for all the three platforms, we can tell they qualitatively differs in how they respond to the packet losses. Now, first, let's look at the GeForce Now bitrate. We observed that the bitrate of GeForce Now abruptly drops to a very low level and stays there when the loss in the network reaches 0.5% or higher. Now, this shows that even the transient events of losses in the network can have outsized impact on the streaming performance of GeForce Now. Whereas on Luna, we observed a relatively stable decline in bitrate with less variation when the losses increased. However, in case of Stadia, the variation remained higher even when there was no limit on no losses in the network. And when the losses increased, the variation also eventually increased in the bitrate. The trend for frame rate was similar across three platforms, and the frame rate dropped as the losses increased. While the frame rate dropped, its variation also increased. Now, when the variation increases for all the three platforms, we observed an increase in freeze of the game stream. So the freeze counts began to increase significantly when the losses increased in the network. With that, I would conclude that in this work, we present DECAF, methodology to dissect cloud gaming performance that measures delay and streaming matrices. We have used DECAF to analyze three different platforms. We showed that the three platforms differ in their delivery strategy and struggle to deliver at 1080p at 60 FPS. And we have also shown the performance cliffs in case of GeForce Now, especially when there is a packet loss in the network. Our findings have implications for users, platforms, and researchers, and our methodology can be used to improve the benchmarking matrices such as the quality of experience models provided by ITUT. With that, I thank you all.